regardless if you are staying for the calculus or not, just want to re-emphasize the purpose of this video is that the gravitational potential change spatially across our equipotential map is our gradient or our slope, and this slope represents our gravitational field. And this is the cool thing, how gravitational field is linked to gravitational potential, is through how it changes through space. And because we're looking at how it changes through space, it's actually important to for the gravitational field lines to be perpendicular to the gravitational potential or the equipotential lines. So here we have a point mass, and there's something wrong with this diagram because I adapted it from a charge. So these arrows point towards instead of away, which are your gravitational field lines. And they are 90-degree angle to perpendicular to your equipotential lines. So feel free to stop here if you understood how gravitational field and gravitational potential are linked. Then the rest of the video I will then talk about the calculus. As you can see, this was obviously adapted from the electric fields or the electricity section, so sorry, please fix this. So here we have the gravitational potential and the gravitational field are related, in which the G field is taking, as we said earlier, taking the derivative of how your gravitational potential changes across space. Don't know why I wrote that again, but anyways, the process kind of looks like this. So we take Vg as negative big G big M over, actually not, don't do over R, do R to the -1, which is the actual exponent. Because what happens if you take that derivative, you know that exponent, and I'm not using proper math language compared to your math teacher, so apologize for that in advance. This exponent pops out to the front. This exponent pops out to the front. Bear with me, you'll get -1 times a negative and times a negative. So 1 negative, 2 negatives, 3 negatives, that's going to make a negative again. And because it's -1, so there's just 1 times whatever, doesn't change anything. But then if you take the derivative of an inverse of a -1 exponent, we also know that this exponent now drops one more level, becoming -2. And lo and behold, it is gravitational field strength, because you get, don't forget the negative, big G big M over R squared. And big G big M over R squared is your gravitational field. And you might be wondering, but there's no negative sign in my data booklet. So what's that negative sign doing there? It has to do with the direction, correcting for the direction. So if you move away from your center of mass, your gravitational potential increases while your gravitational field strength decreases. Another way to think about this is that as you look at a change, as you move away from the point mass, gravitational field vector or gravitational field points towards the center of the mass. So as you're moving away, you're kind of fighting against but you're going against the gravitational field vector, which you see in this diagram is pointing towards the center of the mass. And it's not important for us to articulate the necessity of that negative sign for the purpose of this course, but it technically is the case there. And of course, if you're super savvy, you can even do it the reverse way, just to double check that the math works out by taking the integral of your gravitational field and integrating across space. And if you do that, you should get the gravitational potential. And we know the gravitational potential, the definition is the amount of work used to move an object from infinity to r distance. So when we do the range, the lower bound is infinity, the upper bound is r, from infinity to r, initial to final. And of course, we're going to cut up the G field into small pieces, dr, and then summing up all those pieces all together. Okay, putting in all the equation and the beauty of all that stuff, we get big G big M over r squared. And you're probably thinking about, why am I not putting in the negative sign here, just like I did before? Keep in mind, we're integrating from infinity to r, which is in the direction of the gravitational field. So there's no need for that negative sign, for those of you detailed people. Okay, so from here, we take the antiderivative of a inverse square, which gives us negative big G big M over R. And we find this from infinity to R. Final is big G big M over big R minus negative big G big M over, I'm going to put an infinity sign even though it's not technically allowed. Your math teacher may or may not like that. But the significance of that is the infinity sign means that this whole fraction is going to tend to 0 because you have a really large denominator. Okay, and as a result, you are then left with negative big G big M over R, which is your gravitational potential. So everything all works out perfectly. Calculus is an agreement. I hope if maybe later in this year, when you do learn calculus, you'll come back to this concept again and see how they're all linked together. Otherwise, hopefully these two videos give us some better understanding of what gravitational potential represents. The height does not judge how massive you are. It's independent of mass. So when we talk gravitational potential is per unit mass, we don't care about the mass. It's an objective mapping of the space. And height does not differentiate a hiker from their mass. So you can think of it that way as well. Otherwise, thank you for watching and thank you for staying all the way to the end to watch some calculus. There. Lulu Pig says, hi. Hi. You get a high five from Lulu Pig using his ears. Pew! And a high five from Shen Shen. High five. Pew! All right. And Fat Mama Physics signing out.